So today we're going to look at question number 2 from the 2013 free response part of the exam. Okay, and it's dealing with a particle in motion. Okay, moving on a straight line, and they're giving you the velocity function, and the position of the particle is given by s of t, and you know that s of 0 is equal to 10. So we know the starting position is at 10. Okay, so let's go ahead and answer question or part A. Find all values of t in the interval 2 to 4 for which the speed of the particle is 2. So the speed of the particle is the absolute value of the velocity, okay? That's speed. So we want to set that equal to 2 and solve it, okay? So let's go to our paper and let's write that out. Okay, so in part A, I went ahead and wrote down the velocity function, okay? And so what we want to do is we want to solve the absolute value of v of t, and we want to know when this is equal to 2, okay? So I'm going to put the velocity function into my calculator, okay? And we're looking for where 2 is less than or equal to t and less than or equal to 4. So we're looking between 2 and 4, okay? So I'm going to go to my graphing calculator and we're going to solve this on that. So from our calculator's home screen, we want to press y equals, okay? And then we want to select the absolute value function, which is alpha window and then number 1. And then we're going to type in that velocity inside the absolute value because that will be speed, okay? So we have -2 and then plus and then parentheses and then t squared plus 3t. And then raised to the 6/5. You could do 6 divided by 5 or 6 over 5 like I'm doing. And then make sure we come out of the exponent, okay? And then minus, and then x cubed, okay? Or t cubed. Okay, and then we're going to set our y2. We want to know when this is equal to 2, okay? So we're going to set that equal to 2. We're going to go to our window, and we only want to look between 2 and 4, right? So we're going to set this to 2 and this one to 4, okay? And x scale by 1s is fine, or 0.5 would be fine too. Y-min, let's make this, let's make it like go from like -10 to 10. And you don't really know until you just jump in and try and see what are the settings, okay? Let's do that as the y scale is 1. And let's go ahead and graph and see what we get. Actually, that was a pretty good choice, okay, from -8 to 8. Okay, so right here we want to find, so this is my speed function, right? Okay, so the blue is the speed, and so the red line is when it's 2. So right here we find this intersection, okay, right here and here. So there's 2 times when the speed is exactly 2 in the interval 2 to 4, okay? So we're going to go second and trace for the calc menu, and we want to find the intersection. Okay, so first curve is the speed, okay, and then when it's equal to 2, and then guess, we're going to get that one on the left side first, okay? All right, so we have 3.128, okay? So we're going to record that value, okay? And then we're going to go and do the other one, okay? All right, so let's go second. And you want to record this on your paper. I'm going to go back and record it, okay? And then second, trace for the calc menu again, and then number 5. And then we want to get this one right here. Okay, so I would just want to move closer to that one and just press enter, enter, and enter. And we get 3.473, okay? So I'm going to go back and I'm going to record this on our paper. Okay, so what we got for this was t from our graphing calculator. T was about 3.128. And also when t is about 3.473. And those are the 2 times between 2 and 4 in which this happened. Okay? All right, let's go to part B. So for part B, we want to write an expression involving an integral that gives the position s of t. So use the expression to find the position of the particle at time t equals 5. So there's 2 parts to this, okay? The first sentence and the second sentence. Okay, so we were given that the initial position, right, s of 0 is equal to 10. So if we integrate velocity, we're going to get position, okay? So we want to integrate from 0 to t, okay? And that would give us the position for any time value, okay? All right, so we'll go back and do this. So for part B, we know that if we go with S of t, okay, that's going to equal S of 0 plus the change, right? And the change would be the integral from 0 to t of v of x and then dx, okay? Because that's the t that's represented right here, and that's where we want to stop the integral, okay? So these t's need to match, okay? And then we have to use a dummy variable in here, okay? All right, now, so that's it. We could change the s of 0 to 10 because on our paper we knew that. So we could rewrite this as s of t is equal to 10 plus the integral from 0 to t v of x dx, okay? And if you want to know s of 5, okay, s of 5 would be equal to 10, what we started with, plus the change. And this is the change, right? So the integral from 0 to 5 of v of, and because you change this to 5, you could actually change this back to v of t, okay? All right. I'm going to leave it as x, though. So v of x dx, okay? So this we're going to put into our calculator, okay? And so, and then we'll have what s of 5 is. Okay, and then we're going to probably round this. Okay, so we're going to go back to our calculator and do that. Okay, so from our calculator, we want to go back to y equals, and I want to take the speed off, okay? So I'm going to delete. I'm going to be right on top of this absolute value, and I'm going to press delete. And what will happen is it takes away the absolute value, because now we have the velocity function, and that's what we want, okay? So y1 is now the velocity function, not the speed function, okay? All right, and so I'm going to go to my, back to the home screen, okay? And we're going to type this in 10, okay? And then plus, and then we want to integrate. So alpha window, and then number 4 for function integrate. And we want to go from 0 to 5 of our velocity function. Okay, that's why I wanted to change it and get rid of the absolute value, okay? We want our velocity function. So alpha trace, and then select number 1, because that's where we stored our velocity function. And then at x, okay? And we press enter, and we get negative 9.207. So we'll go back and record that, and that's the position of the particle at t equals 5. Okay? All right, let's go back to our paper and we'll record. Okay, so this came out to be negative 9.207 from our calculator. Okay? And that's it for that one. Okay, let's go to part C. So for part C, we want to find all times in the interval 0 to 5 at which the particle changes direction, okay? So how do we know when the particle changes direction? It's when the velocity function changes signs. So where the velocity function goes from, on our graphing calculator, from below to above the x-axis, or vice versa, okay? From above to below or below to above, okay? So we're going to graph the velocity function between 0 and 5 and see what we get. Before we go to the graphing calculator, though, I do want to do this. Okay, we want to solve for v of t is equal to 0. We need to solve that, okay? Because that will tell me where the velocity is 0, and then if it changes signs at that value, okay, then we know it changed directions, okay? So let's go ahead and go to the graphing calculator and solve this from 0 to 5, okay? Because we do have this 0 less than or equal to t less than or equal to 5, and we're going to look in that interval for where this happens. Okay, so we want to, from our home screen, okay, we want to press window, and we want our x min to be 0 and our x max to be 5, x scaled by 1. Probably y min to negative 10 to 10 is good too. And I just realized I said earlier negative 8 to 8, but it was negative 10 to 10. Okay, and then for y equals, we want to press this. We want to change this from being 2 to being 0, because we want to know now, we want to know where the velocity is 0. Okay, and then let's graph that and see what we get. Okay, so from 0 to 5, okay, before this time value right here, right, where the velocity is 0, and right here, it's changing. So the velocity down here was negative, and then the velocity up here is positive, right? So it changed directions at this t value when it stopped, okay? And then same thing over here. It changed, the velocity was positive, and then it became negative, right? So right here, the velocity changed signs, okay? So I want to find this intersection. So we'll go to second, calc, and then number 5. And then let's get close to this one on the left. And we'll press enter, enter, and enter. So at 0.536, the particle changed directions, okay? And then let's find this other one. So we'll go second, alpha 5 intersect, and we'll get over close to this one. And press enter, enter, and enter, okay? And then 3.318, okay? It happened there too, okay? All right, so let's go ahead and record those on our paper, okay? And that's it for part C. So when we solve this, we got t is approximately 0.536, and then also t was approximately 3.318. Okay, and the question was, when does the particle change directions, okay? So the particle, we write this up, the particle changed directions at t is approximately 0.536 because v of t changed, and it changed from negative to positive at that time value. So at t is approximately 0.536, and the particle changed directions. You could write 2 sentences for this too. Okay, change directions at t is approximately 3.318 because v of t changed directions, or changed, not changed signs, or changed from, let me get my, change signs, okay, would be okay too, okay? Changed from positive to negative at t is approximately 3.318. Okay, and that's answering it. Okay, all right, and giving the answers with the justification that it asked for. Okay, all right, let's go to part D. So for part D, they're asking, is the speed of the particle increasing or decreasing at time t equals 4? Okay, this is asking it, in essence, is it speeding up or is it slowing down? Okay, because speed increasing would be speeding up, and speed decreasing would be slowing down. Okay, so to know if something's speeding up or slowing down, you got to look at 2 things. You got to look at the velocity at that time, and you also need to look at the acceleration at that time. Okay, all right, and then depending on what the signs are of those, you can tell if it's speeding up or slowing down. Okay, so let's go to our calculator, or let's go to the page, and we'll do the write-up, and then we'll figure this out, the values on the calculator. Okay, all right, so let's go to our page. So what we're going to have to find is v of 4, and we're going to need to know what that is. So we're going to need to put 4 into the velocity function that they gave us to figure this out. Okay, now we also need to find the derivative at 4, which is equivalent to the acceleration at 4, to figure out what this is. Okay, and then once we figure out these two values, then that's going to allow us to determine if the speed is increasing or if the speed is decreasing. Okay, all right, so let's go to that right now. Let's go to our calculator and put these in. So we're on our home screen now, okay? And I'm going to clear out what we have, okay? And then what I want to do is I want to find the velocity at 4. Well, we have in our y equals, okay, we have the velocity function, that's y1. Okay, so what we can do is go to our home screen and just type in alpha trace and select number 1. And so this is like v of 4, right? So we want to type in parenthesis and then not x. We want to type in 4, right? And then close the parenthesis. Okay, now so that's the velocity. It's negative 11.456. Okay, so let's go ahead and record that on our paper, and then let's then put in the derivative. Okay, so that would be alpha window, and then 3 for numeric derivative. Okay, so we're going to take the derivative with respect to x of y1, our velocity. Okay, so alpha trace number 1. And then we want to find this, the derivative at 4. And this gives us negative 22.296, okay? So let's go back to our paper and record these two values. Okay, so from our calculator, we got, for the velocity at 4, we got negative 11.476. And then we got for our acceleration, which is also the derivative, we got negative 22.296. Okay, so what do we know? Okay, so the velocity is negative and the acceleration is also negative. So when they're the same signs, that means it's speeding up, which in this instance would mean the speed is increasing, okay? So we would say the speed is increasing at t equals 4 because v of 4 is less than 0. It's negative, right? And, okay, a of 4 is also less than 0. Okay, and that's how we know the speed is increasing or it's speeding up. Okay, that would mean the same thing. All right. Okay, that's it for the number 2 question for 2013. Okay, let's go on to our next problem and we'll do that one. All right. Okay. So question 3 deals with a coffee maker and it's filling a large cup of coffee, and then they're giving you the amount of coffee in the cup for times 0 to 6 in the table format. Okay, so what you know is that at time 0 there's 0 ounces, and 1 minute later there's 5.3 ounces of coffee in the cup. Okay, all right. So and it's given by a differentiable function c. So if it's differentiable, that's going to mean it's continuous, right? And t is measured in minutes, and then selected values are given in the table. Okay. So part A, use the data in the table to approximate c prime of 3.5. Show the computations that lead to your answer and indicate units of measure. Okay. So c prime of 3.5. So we don't have 3.5. We have 3 and 4, right? So we're going to use those two values, that 3 and 4, to figure out an estimation or an approximation of c prime of 3.5. So we'll go to our paper and we'll do that now. Okay, so c prime of 3.5, we can approximate that by finding c of 4 minus c of 3 all over 4 minus 3. Okay, so this is the part that's, we're showing our work. Okay, so that c of 4 minus c of 3, so c of 4 is 12.8 minus, and then c of 3 is 11.2 over 4 minus 3, which would be 1. Okay, so this is just be 12.8 minus 11.2, so that'd be 1.6. Okay, and so what are the units? Well, what are these units for the c, for the function, right? It's ounces. So we'll write ounces per and then minute. Okay, and that's the units for c prime of 3.5. Okay, so that would mean, since this is positive, that would mean it's increasing 1.6 ounces per minute. Okay, all right, or the amount of coffee is increasing 1.6 ounces per minute. Okay, let's move on to part B. So for part B, is there a time t, and with t being between 2 and 4, at which c prime of t is equal to 2, and then justify your answer. Okay, so is there a time between 2 and 4? Okay, between 2 and 4 in which there's a derivative that's 2. Well, if you look, the time difference here is 2, right? 2 minutes. And the ounces difference is from 8.8 to 12.8. That's a difference of 4. So when you take this difference of 4 divided by 2, that's going to give you 2. So yeah, this is going to happen, right? And we're going to use the mean value theorem because between 2 and 4, there's an average rate of change of 2, which means there has to be a derivative in between 2 and 4. That's 2. Okay? All right, so let's go ahead and write that up. Let's do the formal write-up. So in part B, they're telling us that the function is differentiable, right? Okay, so we know C of t is differentiable and it's differentiable from 0 to 6. So it has to be, if it's from 0 to 6, it has to be differentiable from 2 to 4. Okay. And this could be closed, it could be open. The theorem that we're going to use, the mean value theorem, states that has to be differentiable on the open, okay? But if it's differentiable on the closed, it's also differentiable on the open, okay? Because it's differentiable for every value in there, okay? And therefore, okay, because we know it's differentiable, therefore, C of t is continuous on the closed interval 2 to 4. And it has to be continuous on the closed, okay? And then we're going to do this. We're going to find C of 4 minus C of 2 over 4 minus 2. Okay? So C of 4 was 12.8 and C of 2 was 8.8. And 4 minus 2 is 2. So this would be 4 over 2, which is equal to 2. Okay? Now, because this is equal to, and this is an average rate of change between 2 and 4, okay, and because it's continuous on the closed interval and differentiable on the open, even though I wrote closed, okay, therefore, by the mean value theorem, there has to be a derivative between 2 and 4 in which C prime of t is equal to 2, okay? So we can say it, okay? So by the mean value theorem, okay, there must be a t with t has to be between 2 and 4, so we'd say 2 is less than t is less than 4, and this has to be, and it has to be less than, not less than or equal to, okay? So this with t between 2 and 4 such that C prime of t must equal 2, okay? So because of this average rate and because it's differentiable and continuous, the mean value theorem tells us, well, there has to be a derivative that's the same as this average rate of change, okay? And that's the correct answer for part B, okay? So let's go on to part C. Part C says use a midpoint sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of 1 over 6, 0 to 6, the integral of C of t dt, and then use correct units, explain the meaning of it in the context of the problem, okay? All right, so we're gonna do 3 subintervals and we're gonna use a midpoint sum, okay? All right, so let's go to our paper and we'll do that. So we're gonna use a midpoint sum to estimate 1 over 6 times the integral from 0 to 6 of C of t dt, okay? And so this is going to be equivalent to 1/6 times, and we're doing the midpoint sum to find the integral, okay? All right, and we're going to go from 0 to 6, and we're going to do, so these are going to be equal intervals because we're going to do 3 of them, okay? So we're going to go from 0 to 2, okay? So that would be 2 times C of 1, and then plus 2 times, And then we're going to go between 2 and 4, which would be 2 times c of 3, and then plus, and then we're going to go from 4 to 6. So that'd be 2 times c of 5, because 5 is right in the middle, okay? So then this could be approximated by 1/6 times 2 times c sub 1, and c sub 1 is 5.3 plus 2 times c sub 3, which is 11.2, and then plus 2 times c sub 5, c of 5, I should say, is 13.8. I was saying sub, and I should have said of. Okay, now for the AP exam, that's a numeric answer. You're done, okay? That you're done. You don't need to go any further, okay? Now I am going to go further, but you don't have to, okay? So this would be 1/6 times, and this would be 10.6 plus, and this would be 22.4, and this would be 27.6. Okay, and you could stop there even, okay? All right. And then this would be 1/6 times, okay, and then 10.6 plus 22.4. Okay, that'd be 23, so that'd be 33. And then that would be 60.6. Okay. Let me slide that up. So that would be approximately 10.1. Okay, and now what we want to do next is explain the meaning of this, okay, in the context of the problem. Something I need to tell you and make you understand is this, okay? This 60.6 right here, okay, the units on it, I'm going to write it in pen, okay? The units on this would be ounce minutes, okay, or minute ounces. Minute times ounces. Why? Okay, so recall that this 2 right here was actually minutes, right? And the 5.3 was ounces. So this is minute ounces. When you multiply this, this would also be minutes, and this is ounces. So this is minute ounces. This is minutes. This is ounces. So when you multiply them, you get minute ounces, right? Okay, so what are the units for this, though? Okay, so this 1 over this 1/6 came from taking 6 minus 0, okay? Because that's where this came from. So this 6 right here is minutes, okay? So we're taking 1/6, right? Which is 1/6 minutes, right? And if we multiply minute ounces times 1/minutes, right? The minutes are going to cancel, and you're going to be left with ounces, okay? So this 10.1 is ounces. Okay, so what is this? What is the meaning of this? Okay, so let's write 1/6, the integral from 0 to 6 of c of t dt is the it's the average amount of coffee, and it's measured in ounces, between I can't spell between, good heavens. Okay, between t equals 0 and t equals 6 minutes. Okay. You could also say this integral is you have to say average amount of coffee, okay, in ounces, okay, and then you could say in the first 6 minutes the coffee, hot water was dripping through the coffee maker, okay. So you could say like in the first 6 minutes, because that is from t equals 0 to t equals 6 is the first 6 minutes. Okay, let me slide that up. I just realized you guys couldn't see the bottom of it. Okay, so that's what I wrote. Okay, so the 1/6 times the integral from 0 to 6 c of t dt is the average amount of coffee in ounces between t equals 0 and t equals 6 minutes, okay? And that's a sufficient explanation of what this represents, okay? All right, so let's go on to part D. So for part D, the amount of coffee in the cup in ounces is modeled by B of T. So they're giving you a brand new function, okay? A new model for this, okay? Instead of a table, okay? Instead of C of T. So using this model, find the rate at which the amount of coffee in the cup is changing when t equals 5, okay? So this is the amount of coffee. So we want to find the rate at which the amount of coffee is changing. That's a derivative, right? Okay, so we just basically have to find the derivative of b of t, okay? So let's go ahead and go to part D, and then we got to put 5 in it because they're asking you for a specific time, okay? And so let's go ahead and go to part D, and let's find the derivative of b of t. Okay, so I went ahead and wrote the b of t function on my paper, okay? So we want to find b prime of t, and that's the rate at which the amount of coffee in the cup is changing, okay, for any time value, okay? So to take the derivative of this, the derivative of 16 would just be 0, okay? And then we'd have negative 16 times e to the, and e to a power is just e to that power times, and this is chain rule, we got to use the times the derivative of this, right? So negative 16 e to the negative 0.4 t, okay? And then times the derivative of that, which would be negative 0.4, okay? Now, what happens when we do this? We multiply this and we're gonna get a positive, right? So b prime of t is equal to, okay, and 4 times 16 is 64, right? And so it's by 0.4, not 4, so that'd be 6.4. So this becomes 6.4 e to the negative 0.4 t, right? Okay, so they're asking you to find this at b prime of 5, right? So let's come over here and let's write b prime of 5. Okay, so b prime of 5 would be 6.4 e to the negative 0.4 times 5. Okay, so negative 0.4 times 5 would be negative, it would be 2, right? Well, negative 2, okay? So this would be 6.4 e to the negative 2, or 6.4 times e, 1 over e squared, or 6.4 over e squared, right? Now, what does that mean? Okay, so this is a positive value, right? That means the amount of coffee is increasing, okay? That amount per minute, okay, at t equals 5, okay? So if they ask you to what's the meaning of this, okay, and we're done, right? We've answered the question they asked for. This would be in ounces. I should say this. This would be ounces per minute, okay? But what this represents is at t equals 5. I'm going to go ahead and write this, okay? I know they didn't ask this, okay? At t equals 5, okay, the amount of coffee in the cup. And since this rate is positive, it's increasing. And that's the amount it's increasing. So 6.4 over E squared ounces per minute. Okay. And that would be the interpretation for this derivative. Okay. So we did an interpretation for the average value of the function. That was part C. And then we did this for the interpretation of the derivative. Okay.